from Technical University of Dresden in Germany. The talk is about density-dependent pore water pressure evolution in a simple cyclic shear test.
I will talk today about the interpretation of pore water pressure evolution on a slightly different way than we are probably used to it. And I will introduce today in my presentation a simple cyclic shear test for density-dependent pore water pressure evolution. Now we know that pore water pressure builds up or occurs, pore water pressure evolution occurs in saturated cohesionless soils. When subjecting these soils to external loading, pore water pressure is evolving and causing the decrease in effective stresses and therefore also stiffness and shear resistance. Now, if we consider the same sample preparation method, and if we test different soils under the same conditions, then we can safely say that different sands will respond differently to the same loading. Therefore, we are safe to say that pore water pressure buildup or its tendency to soil compaction depends on the soil granulometry. And then here we would be able to think of a test that will enable us the comparison of the sensitivity of different sands to density-dependent pore water pressure. And of course, we all want this kind of test to be simple and we have a simple procedure and to be quite fast. In the following minutes, I will introduce such tests. The idea behind the cyclic shear test I'm going to talk about today is very simple. We are considering a cylindrical specimen, but without water-filled cell. As you can see here, as you can see here on the right-hand side, the schematic representation, and left-hand side and the right-hand side is denoting shows actually the installed specimen in the experimental setup. Now, this specimen is loaded in horizontal direction cyclically with a defined frequency and loading amplitude. And you can see here the analogy to a simple shear test. Due to this loading, the specimen is swinging in horizontal direction, and it causes this loading causes the evolution of pore water pressure. The evaluation of the test is very simple, and it follows from this very simple equation of effective stress. Now, the performance of the single test, I will explain using here the schematic representation on the left-hand side, and I will support my explanation using the small diagram on the right-hand side. The x-axis of the diagram is denoting the loading cycles, while the y-axis is showing the evolution of pore water pressure. As you will later see, it's also at the same time the evolution of effective stresses. At the initial state, highly saturated sand sample is installed by pouring a sand-water mixture using a funnel in a supported rubber membrane. At this step, at the initial state, the pore water pressure is equal to 0. The effective stresses are equal to 0 if we neglect the cell plate of the soil. And the only pressure that is acting on the specimen is the relative air pressure in the testing facility, and this is also equal to 0. The relative air pressure remains constant and unchanged during the test and represents the total stress during the test. The next step, in order to consolidate the specimen, the suction or negative pore water pressure is applied to the bottom of the specimen. By applying suction, due to the 0 total stress, we increase the effective stresses to the value of the suction. And finally, in the third step, the cyclic loading of the specimen is performed on the top cap of the specimen in horizontal direction with a defined frequency and loading amplitude. And due to this loading, the pore water pressure is evolving, causing at the same time the reduction of effective stresses. During the test, pore water pressure is measured at the bottom of the specimen and evaluated. And also additionally to this, we use 2 lasers for contactless measurement of the deflection of the top cap in horizontal direction, and the second laser is used for measuring the settlement of the specimen. The duration of one test is approximately 30 minutes, including the specimen preparation procedure. And from the test, we are interested in the rate of pore water pressure buildup, the CL value, that is linked to the initial relative density of the specimen. Now, the evolution of a single test, I will explain in more detail. On the left-hand side, you can see the raw data or the evolution of pore water pressure within one test, plotted against the number of cycles. Now, in order to obtain a dimensionless rate of pore water pressure buildup, in first step, we normalize this data using the initial value of the pore water pressure and determine the CL value as the slope of a second line in this normalized graph. When performing several tests in one sand for different initial relative densities, as you can see here in the presented graph, it is obvious that the rate of the pore water pressure buildup depends on the initial relative density, and as it's also obvious, it's decreasing as the initial relative density is increasing. Now, for each one of these tests, we can determine the CL value. When plotting the CL value against the initial relative density for these different tested specimens, we see that obviously there is an exponential decay between the CL value and the initial relative density. Now, to quantify this dependency, we can also plot this data in a similar rate of representation, and obviously the dependency now becomes linear and can be approximated using a linear regression. The quantification of this dependency can be expressed to the regression coefficient, the KL value here, and considering some reference value of the initial relative density, we are also able to find a reference value of the rate of pore water pressure corresponding to this reference value of the initial relative density. Now, taking into consideration the KL value and our reference value of the pore water pressure rate, we can determine the rate of the pore water pressure buildup at any given density, considering this exponential relation denoted on the graph. And what happens if we consider several sands? For simplicity, I will talk here about two different sands. Those sands are sand A denoted with a straight line and sand B denoted with a dashed line. Now, if we consider the density 1, we see that, I'll try this now. Okay, yeah. So if we consider the density 1, we see obviously that the CL value in case of sand A, the red dot, is lower or smaller than the CL value in case of sand B, the blue dot. It means further on that by testing these two sands at this density 1, the sand A is less prone to pore water pressure evolution than sand B. If we densify these sands to density 2, we see obviously that the CL value in case of this density is the same for both sands. This means that by densification or when testing these sands at this given density, they will both show the same sensitivity to pore water pressure buildup. Now, it is obvious that the difference between these in CL values between these densities is different in these two sands, case of these two sands, as the KL value is also different, which means further on that the sand B has larger KL value, as can be seen also here. This further on means that by densifying these two sands from density 1 to density 2, sand B is experiencing larger change in the pore water pressure, in the rate of pore water pressure buildup, and therefore it is much easier to influence the sensitivity to pore water pressure buildup of sand B than of sand A. Now, before I show some real experimental data, I want to introduce 3 different sands used in this study. Those are sand 1, which is coarse grain sand. Sand 2 and 3 contain different kinds of grains and also very, very small amount of fines. All sands were installed underwater, and in case of different densities, acidification was achieved by applying tapping to the installation mold. They were all consolidated to the same pressure of 60 kPa, and the geometry was the same in all cases, and also the loading conditions. Now, I presented here the results in this sum-logarithmic representation showing the dependency between the initial relative density and the CL value. And as we can see here, obviously that the KL value, this regression coefficient in case of SAN 3 is larger than in case of the SANs 1 and 2. Also, it is noticeable that the initial densities here in the loosest state fall in a middle dense to dense range. I still want to notify here that these are still the loosest possible states according to this distillation method. But when determining the initial relative density based on the conventional limits of the density, they fall into this middle dense range. There is also obviously some scatter in the results. We are working on clarifying this scatter. Most likely, the scatter comes from the saturation. In order to compare the results, to compare the SANs among themselves, I will perform the comparison at the initial relative density of 0.6 and then again at 0.75. Now, obviously, when comparing these three SANs at the initial relative of 0.6, we see that the rate of the pore water pressure buildup is the highest in case of SAN 3, meaning that this SAN is at this given density the most prone to pore water pressure buildup. And this sensitivity is decreasing as we are moving towards SAN 1. If we compare the comparison now at the density of 0.75, we see that the CL values at this density are very similar and relatively small in case of all three SANs. Which is also noticeable here that in case of SAN 3, SAN 3 is experiencing the largest change in the CL value when densified from 0.6 to 0.75, and this is also expressed with the largest value of the KL parameter. But the conclusion here would be following: at the given density or at the relative density of 0.6, the SAN 3 is the most prone to pore water pressure buildup, and also when applying a densification as a countermeasure to pore water pressure buildup, it is possible to, it is the easiest, in case of SAN 3, it is possible the largest amount of change of pore water pressure buildup between these two densities. Now to conclude, I hope I was able to convince you that the presented Cyclic test provides us a possibility for fast testing of pore water pressure buildup with change in soil density. The test delivers the rate of pore water pressure buildup, the CL value, at a specific initial relative density, and also enables its comparison for different soils. Further on, it gives us information on the change of the rate of pore water pressure buildup by soil classification, which is expressed through the parameter KL. And finally, I hope that this test might be an index test, as it is offering us an opportunity for fast comparison of different SANs with respect to density-dependent pore water pressure buildup. To conclude today's presentation, I would like to direct your attention to the lecture of Professor Casagrande from 1971 on liquefaction phenomena. In his lecture, Professor described a simple cyclic test, which he considered useful for demonstration of soil liquefaction in laboratory, and he termed the test the Pore Boy's simple shear test. And I quote now: "In this method, the center of the triaxial specimen was oscillated laterally by hand to failure." I think there is an obvious similarity to the presented test today. The only difference is that we don't apply loading by hand, but by a defined loading frequency and the amplitude. And thank you for your attention.
Thank you very much.